Hi, MES 201 students. I told you I'd give you some help on telling your story with the beam data. And so I wanted to get this video out to you so you'd have it over the weekend. So here's what I'm going to do. I'm going to give you just a little bit of big picture help, tell you some things to think about, and then I'm going to show you a video I made a couple of years ago that I gave to students after they turned their beam data in. And so I go through what they turned in. And so I talk about it and I talk about things that worked, things that didn't work, and kind of go through an explanation that way. And I think that'll probably be the thing that's going to help you the most as you try to put your slides and get your story together. Now, one thing I want to tell you, remember that what you're going to see, I did after they turned it in. And so I talk about their presentation. That's your final presentation. And I'm going to give you more help in putting that presentation together. But one of the things that I say in the video is I tell them you're not going to have this many words on your slides for your presentation. I'm talking about your final presentation. What you're doing right now, you're going to have words on it because you're putting words that are outlining what you would say about that slide to tell your story. Okay, so just some general information about telling your story. You want to keep in mind that you're really doing a technical presentation. You've done some technical work and now you're presenting that work. You have something in your head that you want to get into someone else's head. So what you want to do is you want to stop and think about, okay, what is my purpose? And I like to think about it like design. What is my purpose? And now design the big picture of, okay, what do I need to tell somebody to accomplish that purpose? So that's your big picture. So like storyboard it, think of outline, like what are the big things that they need to know in order for me to accomplish that purpose? And then go to each section and begin to say, okay, if I'm going to get this point across, what do I need to tell them? I had the purpose of I did an experiment and I was analyzing what mattered for modulus. And what did I learn? What is in my head that I have learned about that? And so now, how do I tell that story to somebody else? For them to learn what I learned, for them to have the final conclusion and know, okay, here's what you can expect for modulus out of our 3D printer. Here's what you can expect about the different fill rates. Here's what you can expect about orientation. What do they need to know to learn what I learned about it? And then you tell your story. You step them through, okay, they need to know this, and then that will allow them to get this conclusion I want. They need to see this and this. And so there's no magic other than just don't rush into it. Deliberately stop and think about, okay, what is my story? How did I get to this final conclusion? What were the little conclusions along the way that brought me here? And how do I tell that to someone else? And remember, they know nothing. So don't assume anything. And you have to think about who your audience is. In this case, your audience are engineers. So you want to talk to them like engineers. They don't need to know every little bitty thing you did. That's where you have to think, okay, in an engineer, what are they going to want to know about I tell them this conclusion? What are they going to want to know to trust me? How do I tell that story so they can see that my conclusion is solid? And so that's the big picture as you're putting it together. And like I said, the rest of this video is just going to give you examples of what other people did, and you'll hear me talk about it. And hopefully that'll help you put your story together.
So once you have all the averages and the standard deviations, then it's just a matter of doing the manipulations, putting your story together and telling it. So what I'm going to do now is jump and pull some slides from what you all turned in and just give you some points for bringing this information together, presenting it that you can use on your final presentation. One note for sure, make sure you watch that presentation. Technical presentations are very different from what you've done, speeches, that kind of thing in the past. So you want to watch that video and use that information to put together your presentation and tell your story. Okay, so most people took two approaches when working with this data. One, kind of like I did, they started with 30 and 100. They showed the average for it. There's an obvious difference. Then they went and looked at the average for 30% side and up, saw that it was close, did the t-test, proved yes, there is a difference, and then the 100% side and up, and either looked at that and said it's obvious there's no difference, or also did the t-test and said yep, there is no difference at all. So that's one approach people took. The other approach is some people started with fill, and they said, okay, here's 30% side and up, and yep, the t-test confirms that that matters. Then for 100% side and up, no, it doesn't matter. And then they went to the 30 versus 100, but notice what they did. They put 30 side, 30 up, and then 100 side and up together. Why did they do that? Because they showed that fill did not matter for 100, so that meant it was fine to average all of those together. And then they made the case, see how the error bars, the confidence interval on the average, there's no overlap whatsoever. So 100, fill, and 30 are definitely different. Fill rate mattered. Okay, whichever approach that you took, people came to the same conclusion that fill rate definitely mattered. Orientation mattered for 30%. It did not matter for 100%. That's great. One of the objectives of our experiment was to determine that. But the other objective was to understand what E is so we could use it when we're doing designs. So most of you left that piece out. You did this well, you drew these conclusions, but you didn't take that last step and present these final conclusions. So you should have presented, okay, 30% has an E of this when it's on its side. It has an E of this when it's in its up orientation. And 100% has an E of this no matter what. So you definitely want to make sure your final conclusions, if you're trying to come up with what is E or whatever, that you present that. Okay, but one of the things I want to make sure I point out to you on this is, number one, this unsure if orientation matters, I probably wouldn't say it that way. If I was going to say anything, I would have said there's no from our data, there's no reason to believe that orientation matters. And we'll talk about that in a few minutes when we kind of go through some of the t-test examples. The other thing I wanted to point out is when we calculated our averages back with the pivot table, we had 30 side, 30 up, and we had the standard deviation, and we had how many we had. Now remember, that's the standard deviation on individual values. We also can calculate the standard deviation of that average by that divided by the square root of that, okay? Now, this right here, notice they use this standard deviation on x's correctly, because we're saying here's what you could expect from E from any individual beam that you pick up. And so remember, anytime you tell me the results of an experiment, here's what you can expect, you need to let me know the uncertainty so I realize how much variation is in that number when I use it. And then they correctly used that for 100 and that for 30 up, okay? So this one piece a lot of you guys left off, so in your final experiment, just don't forget this piece to report everything about your objectives. Okay, so now let me just show a couple slides and just point out some things. So for one, showing 30 versus 100, there's really two approaches to do it. One is you show them both on the same graph on top of each other. The other is you show them more on a line graph where this could be a line graph too, but you show them where they're spread out like this. There's no one right way. If the data has a big difference between it like this graph works well. If there's not as much difference and these points are intertwined with each other a lot, I find this way works a lot better because then you just see the rectangles overlap a lot more. It's totally your preference. In this case, putting them like this, I think works very well because it makes it really obvious that the 100 is larger almost all the time, except for maybe a few of these little stragglers. Okay, something else over here. Notice when I pull those boxes off. Again, personal opinion, it really helps draw your attention to these groups when you have those on there. So I think it's worth that little bit extra to put those boxes on there if you're going to put it in this form, just to help tell your story. Because what you're trying to do is you're trying to best tell your story to draw the reader's attention to what you want them to see. So anything visually you can do to help that is a good thing. Okay, the other thing I wanted to point out, whichever form you show, I always like, when possible, to show this and then the averages of it. This is nice. Engineers like data. This shows me the raw numbers. It shows me the consistency. This makes it much more clear that there's no doubt about it that there's a difference between 30 and 100. Much more than this. You know, you see how big these rectangulars are apart, or how big that is. When you condense this down to the average, though, it's obvious. It's a no-brainer. Now, again, I still like to see this, but this with it. So usually I'll put these two on the same chart to tell that story about the big picture piece. And kind of like I said in the video, I probably would have started with these two charts. I would have shown my big picture this way. And one of the key things you want to make sure that you do, and that's why this picture is important, you need to make the case for why it's okay to take the averages for each of those treatments. It's okay to take an average of 30 side. It's okay to take 30 up, 100 side, 100 up. Later, you're going to make the case, okay, I showed that orientation didn't matter here, so it's okay to take the average of all of those. But that's just why I kind of like this picture, because at the same time I can make the case, the consistency there, so it's okay for me to take an average and put a confidence interval on it, because I've got the only thing going on in there is random variation. Okay, something else I wanted to point out. One person had this graph, one person had this graph, and notice that they're the same thing. It's both the 30 versus 100, 30 versus 100. But notice over here, the error bars don't overlap at all. And over here, there's a lot of overlap. Okay, so what's going on? Here's what's going on. Over here, this person correctly used this as a standard deviation, and they multiplied it by 3. They're comparing averages with a confidence interval on the average. So you got to use this standard deviation of the averages. This person over here incorrectly used this standard deviation. So they were comparing averages with a confidence interval on individual readings. So that's why this confidence interval ends up so much bigger, because they used it on individual values instead of the one on X bar. So just be careful. Make sure when you're trying to compare averages, you need the standard deviation of the averages. That's why this one said error bars 3 times standard deviation. Standard deviation of what? That's why you'll always see me say S of X or S of X bar to differentiate standard deviation of individual values versus averages. Okay? Okay, so another one. Watch the order when you're doing these graphs. This graph, it doesn't say it, and you probably should. It was sorted by run order, and then it showed 30% and 100. This one right here, I don't know what order it was sorted in, but it wasn't run order, because notice this graph and this graph should match, but they don't. Notice these 3 points down in this range. Those points are over here, but notice how they're spread out. So it makes the whole shape look differently on it. So just be careful about how you sort and then tell that on your graph. Okay, also, use the tools you know to make good graphs. You're trying to clearly communicate something visually. So notice here, all those right there, how it clutters it. See how much nicer this looks when you just have the 30 and the 100. Remember, with a line graph, you can have a column, and whatever you put in that column, you can tell it to show down here. So this person did that and just put 30 and 100 instead of using the column that had that in every single row. So just visually pay attention to those kinds of things. Okay, also on this graph, they had error bars t times sx. Two things I want to point out. Number one, this should not be sx. It should be sx bar because you're comparing averages. So that's the confidence interval of averages, not x. The other thing, don't use t. And again, I'm sure you did this because when I was doing the lecture explaining this to you guys, I did t. The reason why I did t is because in my spreadsheet it was variable and I could change it. I was just pointing out that it's the thing you're multiplying by. But when you're actually showing the graph, put 2 or 2.5 or 3 or whatever you use to create these error bars so the person can specifically see, okay, that's 3 times s, the standard deviation of x, and like I said, for this graph, it should be x bar. There should be the line over it. Okay. Having really pretty backgrounds looks really nice, but you have to be very careful with it. When I first saw this one, I really liked the image, but I thought, oh no, it's going to have this on all the slides and it's going to draw the attention away. That wasn't the case. Several of you had nice opening slides like this, but then what you had afterwards didn't pull your attention away. So for example, like this slide right here, when this first comes up, this floor pulls my attention away. You don't want the background, things about your slide to pull attention. You want your slide to draw attention to the main thing that you're trying to show. This slide does it too. When it first comes up, the red, the brick around the side, it pulls my attention away. You don't want to do that. Notice this slide. I really liked this one. This brown background, it made a nice look, but this gray and then especially this bar around the graph, it almost like centered me in and immediately brought my attention right to that graph. And that's what you want to do. So just be careful that the backgrounds or whatever you choose for your slide, it draws the attention to what you're wanting the person to show. Because the whole point is trying to use visuals to communicate what you want to communicate. Okay, even this one's okay. It doesn't have a fancy background or whatever, and that's all right, because still, where does your attention get drawn? It gets drawn to the graph and then the few words over here. And we're going to talk about how you would definitely not want this many words on your presentation slide. What I asked you to do for this was to tell me your story, so I expected a lot more words. Okay, just a couple other tips. One, this person did a really nice job. Does orientation matter for 30%? Bam! Yes, right there it does. Some of you in your story, it took a while to get to the major point. It's always better to hit your major point first, and then if you want to explain a little bit and say, yes, it does. Now, by just looking at the graph, we couldn't exactly tell, so we had to run another test. But get your main point out there right away. Something else I wanted to point out, I said I'd come back to the t-test. So this person does a nice job explaining. They say the t-test showed there's only a 0.54 of this happening. What that p-value really means is it means there's a 0.54% chance of these averages being this far apart if the two averages were truly equal, if the distributions were equal. In other words, if orientation did not matter. So let's stop and review real quick just what the t-test really is saying when we get that percentage. So here's the results or the output from Excel on the t-test of side versus up for the 30. And remember what we've said, that the central limit theorem guarantees us that the averages are normally distributed. And so what we do with the t-test is we say, okay, what if we subtract those two averages? Well, the subtraction, that distribution is also normally distributed. It should have an average of 0. And so what we do, the t-critical, that is the value right there that represents our alpha level. So if we did a 95% t-test, that's 2.5 on that side, 2.5 on that side. And we always do a two-tailed just to be conservative. We're saying the means are either equal or they're not equal. Not equal means it could be bigger, smaller. We're going to let it be on either side. So that's what that t-critical is. And then The t-stat is the actual difference between the two averages. So it's the difference between these two averages divided by the standard deviation of the combined. How many standard deviations are we away from 0? So that's where it brings in that idea of between variation and within variation. How far apart do these compare within how much variation there is within? So that's that guy. So you see in our case, we're way beyond what we would expect randomly. How far beyond? Well, that's the p-value. The p-value is the probability of getting this value or beyond. And it's actually this and also the area over here. So just this one side is even half of that. And like I said, we're conservative. We always use the two-sided to be conservative. So what that's saying is that there is a 0.5% chance to get a difference this large if these two data sets were the same. So what that's saying is these two data sets are not the same. So orientation matters. There's only a 0.54% chance of them being that far apart if orientation didn't matter. So yes, it does matter. And so that's a good way for you to go and say that. Okay, I said I'd talk about this earlier. Again, and here it is. For your presentation, you do not want words like this on your slides. So for this slide, does orientation matter? I would probably have yes. T-test, 0.54%. That's probably all I would have on that slide to use it then to tell my story about this. You don't want all these words clogging up you trying to tell me what you want to tell me about your story. Okay, and then does orientation matter for 100? No. And this is a pain with hypothesis testing. Because here's what this is saying. That there's a 52% chance of the averages being that far apart if the two averages are equal, if orientation did not matter. In other words, there's no reason to believe orientation matters. There's a 50% chance that could happen just randomly, so there's no reason to believe orientation matters. I can't say orientation doesn't matter. I just don't have enough evidence to say it does matter. See, accepting that null hypothesis is a weak thing. So, like I said, it's really kind of statistically, all I can say is there's no reason to believe orientation matters, okay? So that's why I said on that one slide, not enough information. I'd probably say it a little differently. There's no reason to believe that it does matter. So just looking at the same visual for this one, you see the T critical is right there. It's still about 2. Our calculated T is about a half a standard deviation, 0.6. So you see it's right in here. And remember, it's two-tailed. So that's why the negative versus the positive, it's just saying it's lower than higher. So that's why I can go on this side instead of down here on the negative. And then our P, that 52%, that's saying right here. So if these two averages were the same, what's the chance of getting a point right here? Well, a lot of chance, 52% of chance. So you see, but that shows you the correlation between here and here. And the whole idea with the t-test, which is why the next approach I'm going to show you isn't appropriate, is it's not how far are these two apart, it's how far are these two apart between here versus how much variation is there within here. That's the difference. You're looking at how much variation would I expect between two averages, that S of X bar combined, versus how much variation really is there. So that's what you're going to see in this next approach, what it doesn't take into account. One last thing I want to clarify before we leave this t-test and the graphs. A couple of people did something like this where they pulled up the t-test and then they said since the mean increased by 13%, that means that it did seem to benefit. Okay, now calculating the percent increase from one thing to another, say from up to side or from 30% to 100%, that's not a bad thing, but you can't use that percent increase as proof that something mattered or not mattered. Because it doesn't matter how much percent increase there is from here to here. What matters is how much percent increase is there from here to here based upon how much variation is there within here and within here. It may be when you look at the points within here that some of them differ by 20%. So having a 13% difference from here to here means nothing. That's the whole idea of the standard deviation, the within variation with between variation, and that's what the t-test is sorting out for us. So that's why we have to say, okay, let me look at the t-stat versus what I would expect here. And this tells me the probability of that happening by chance, of me getting that many standard deviations away from the average by chance. The two averages being that far apart by chance. There's a 0.5%. So yes, calculating the percent difference is a great thing, but you can't use that as a conclusion for saying two things are different. So I just want to make sure that none of you are left with that confusion, that the t-test is sorting out within variation from between variation. A percent difference is just looking at the difference between the two. So for your semester project, you've done the step number one. You've done a good DOE, you've designed your experiment well, you've sorted things out so that when you bring your data up, the only difference between the two different pieces are going to be the thing that you changed. You've done that well. Don't forget when you first take your data, take a measurement, stop, look, make sure it's what you think before you take all of it. When you get done, plot everything you measured in run order or sorted by the different levels in run order just to make sure your data is valid, and then come and do this step right here. And from what we've seen, remember, first just look at your data visually. Listen for what it's telling you. Use your engineering knowledge, predict relationships, sort it in different ways in a line graph just to see what it's telling you. Sometimes it's helpful to look at absolute, sometimes percent. Once you know repeat measurements are random, you can average them and then begin to look at the averages. We saw that when we saw side and up. Yep, they were random. Then we looked at the average. It was much easier to see that difference with the average. Once you know that your independent variable doesn't matter or a level within it, average that over. And how do you tell? Well, that was the purpose of this assignment. You learned 3 different tools. You can look at it and the individual levels and it may be obvious, or you can calculate an average and put a confidence interval on the averages and compare those. If they're still too close to tell, then you can use the formal t-test. So each of those tools, which one do you use? You use the one that you need to use. It honestly never hurts to use the t-test just to be able to say, there's a 52% chance that happened by chance. There's not enough evidence to say that there is a difference between the two. And then last, make sure you draw your final engineering conclusions. All that's giving you the information to know what matters, what doesn't matter. Then draw your engineering conclusions, say what matters, say what you can expect, whatever it is you're trying to get from it. So one last thing I wanted to show you. If you need help, feel free to reach out and I'll be glad to help you with it.